All right, let's get her started. We're on, this is math 66. Shit, I don't even know the name of this section. What section is this called? I wrote 10.3, but I don't think it's 10. That shit, it is 10.3. Oh well, let's do it. Back to that. 10.3 is on doing things like length, like arc length, and area with polar coordinates, or a polar parameterization, because that's really what it is. So this like just incorporates a shitload of stuff. Right? It just keeps coming back. Why do you think I keep bringing up, like throwing in problems, and and it gets even better when you get to Calc 3, and now we're doing arc length over 3D. This is an unending topic in this area. All right, so a couple things we did with parameterization that we'll find helpful. Previously, we looked at finding dy dx, and we saw that that was dy dt over dx dt. But t is just a variable here. I could just as easily say dy d theta over dx d theta. Now we saw that we could have things like, remember, like we were doing graphing of shit like 1 plus cosine theta and things like that. So the point here is like r is literally a function of theta. Or r equals like f of theta. But I hate using f because we used f for y and x. So like I'm just going to call it r of theta. So if we look at our two polar setups, x equals r cosine theta and y equals r sine theta, what happens if we take the derivative of theta with respect to both sides? I should do it right. Put dd theta in front of it like this. dd theta in front of it like that. I hate doing that. I always forget to do it. I always forget to add that I need to give space for it. So maybe I'll rewrite it so it's a lot cleaner. R sine theta. It's of y. And r is a function of theta here. So we have two things that are related to theta. We got to do a product rule. So if I take the derivative of the first term dx d theta is going to equal dr d theta times cosine theta plus r times the derivative of cosine is negative sine theta. And a lot of times people write this in the other order, putting negative r sine theta first. And I'm going to say r prime. But just remember, when I say r prime, I'm talking about with respect to theta. If you want to use dr d theta instead of r prime, please do. We'll do that over here. We have dr d theta times sine theta plus r times the derivative of sine theta is cosine theta. And so if I wanted to rewrite the order here, I just put the r cosine theta first. plus r prime sine theta second. Which means when I put this shit together, dy dx is this r cosine theta plus r prime sine theta over negative r sine theta plus r prime cosine theta. And I'm going to say, bless your heart if you try to memorize this. There's a lot there to memorize. It's easier just to do the product rule on x equals r cosine theta and y equals r sine theta. And memorize long term. Like what you retain in your long term memory tends to, unless you got a, let's face it, a phenomenal memory. It's shit you practice a lot. And like practicing a lot, this a lot is time consuming. It's hell. It's easier just to take the derivative. Let's take a look at an example. Are we ready? Nope, people are still writing. No yawning, Dad. It's barely 4:20. It's not time for nap time. Because I'm boring. Yawned at me. It's cold, Dad.
Cold and calculating.
All right. People look like they're done writing. Let's take a look at r equals. What do we want to go with here? What sounds like a fun function? I said 1 plus cosine theta a little bit ago. Let's do that. Let's find the slope of the tangent line. At theta equals pi over 6. So we're looking for dy dx. We want dy d theta over dx d theta. And we know that there is some r primes in there. So let's take the derivative of this with respect to theta. What is the derivative of r? negative sine theta, right? So we had dy d theta or dy dx. When we clean that up, we just did it, so I'm just gonna grab it. We had r cosine theta plus r prime sine theta over negative r sine theta plus r prime cosine theta. And let's replace that with what we have. R is 1 plus cosine theta. Times cosine theta. Plus r prime was negative sine theta times sine theta. And on bottom, I have negative r, so negative 1 plus cosine theta times sine theta. Oh, I wanted that in blue for what wasn't changing. Plus r prime was our negative sine theta again. And this time times cosine theta. So if I clean that up, I have cosine theta plus cosine squared theta minus sine squared theta all over negative sine theta plus, nope, minus sine theta cosine theta minus another sine theta cosine theta. There's negatives all over the place on the bottom. I'm gonna factor out a negative and make all that shit positive, just so I don't have a lot of fucking sign mistakes. That seems like a good idea. We can clean up some of this before we plug in theta. Does anyone remember what cosine squared theta minus sine squared theta equals? That's cosine 2 theta. Excellent. And I have sine theta. There's a negative. Let's put the negative out front. Put it in blue so it shows up differently. And it looks like I've got, this is 2 sine theta cosine theta. What does that simplify to? Sine of 2 theta. So now that we have that, we can evaluate that at theta equals pi over 6. Cosine of pi over 6 is root 3 over 2 plus. So if I do cosine of 2 theta, that's cosine of 2 pi over 6, which is pi over 3. And that's 1/2. Cosine of pi over 3 is 1/2. On bottom, I had sine of theta. Sine of pi over 6 is 1/2. And this one is root 3 over 2. Which, interestingly enough, equals 1. I am missing the negative sign. if I wanted to find where the derivative equals 0, let's find the horizontal tangents. There's another form of cosine 2 theta that is just in terms of cosines. This is 2 cosine squared theta minus 1. That is. So if I put that in, the top could be 2 cosine squared theta plus cosine theta minus 1. We're going to do over sine theta. I'm going to leave this alone for now, because horizontal tangents will be where this equals 0. And that's where the top equals 0. So let's solve this, and then we'll just verify that it doesn't make the bottom 0 at the same time. Let's solve that. This might be a little bit easier as u equals cosine theta. Do 2u squared plus u minus 1 equals 0. I want a plus 1 here and a minus 1 there to end up with a plus u total. So I get u equals 1/2, which is cosine theta equals 1/2, or u equals -1, which is cosine theta equals -1. This looks like this occurs at theta equals pi over 3, 5 pi over 3, and this one will be theta equals pi. So plugging in pi over 3 is going to give us sine of pi over 3 plus sine of 2 pi over 3. Those are both positive terms. Without calculating what they are, they're both positive. So pi over 3 has got to be okay in the bottom. There's no way to get a 0 if they're both positive. If I do 5 pi over 3, they're both negative. Sine is negative down in the fourth quadrant. So those are both negative. There's no way to get a 0 when I add two negatives together. If I stick in theta equals pi, I get sine of pi and sine of 2 pi on bottom. Those are both 0. 0 plus 0 on bottom. This one is rejected. And if you graphed this, this was the cardioid that did this. So we kind of found like right here. We just found right here. And this is pi, and we can see it's got a cusp there. So the derivative's fucking all wonky and shit. And it changes signs depending on how we're going through theta. Any questions? Okay. I'm sure everyone has a chance to write that down before we move to arc length. Yay, arc length. So you guys ready? So what was the parametric form of our arc length formula? You want to remember? With T.
So. Where. The X squared plus dy squared.
Excellent. And then a dt. Well, theta isn't any different. It's just a different parameter. So we have dx d theta squared plus dy d theta squared. And then a d theta. But we actually have shit for those. Dx d theta was the denominator we had over here. Negative r sine theta plus r prime cosine theta squared. That's my dx d theta. And my dy d theta was r cosine theta plus r prime sine theta squared. Theta. Let's just figure out what this inside is before I put it back in. I'm going to ignore the integral right now, the square root. Let's square this. If I square this one, negative r sine theta squared is r squared sine squared theta. And then we have the product of the two, multiply them together, and there's two of them. There is a minus 2r r prime sine theta cosine theta. And then we have that squared is going to be r prime squared cosine squared theta. And then we'll do this one. I'll do this one below it in blue. If I square the first one, I've got r squared cosine squared theta. I'm going to put that with the r squared term. I'm going to line that up with it. Because we're adding these two together. And then I have to have 2 times the product is 2r r prime sine theta cosine theta. And then I have r prime squared sine squared theta. That's all inside the radical. We'll put the radical and the integral back in a second, but give me a second to write that down before we start looking at what cleans up here. What's wrong, Dalton? What's wrong? Nothing. Anything clean up here? If so, what? One of them is glaringly obvious. What's the easiest thing to spot here that cleans up? If that's the easiest one, fuck it, let's do it. This has a r squared and then a sine squared and cosine squared. So I could factor out the r squared on that. I could also do the same thing on this one, right? So that addresses these two and these two. What about the two in the middle?
It's probably opposites.
They're opposites, right? They cancel. So this is all we got. And what's sine squared theta plus cosine squared theta? 1. So this entire integral reduces down to L equals the integral from, we'll say theta equals alpha to theta equals beta. We have r squared plus the r prime squared looks kind of funny. It might be easier to write it as dr d theta squared. Arc length and polar. And this seems like a lot of work, right? We even had to start off remembering what dx d theta and dy d theta were. If you didn't remember what those were, you'd have to rederive those. This one is easier to memorize than derive. So this one is worth memorizing. There's an alternative way of looking at it. That's the geometrical approach. But it stems from doing the same thing as that we did with ds turning it into dx and dy, but I'll show it to you. Let's say we got some curve going like that. And we're going from there to there. So this is like a d theta. And if I say this first theta is alpha, and this one is beta, or part 1 to part 2, I'm going to make a circle going off of alpha. I'm going to treat this as a radius r, go like this. I have a radius r. And for a small enough circle, not small enough circle, for small enough d theta, that blue wedge looks like a triangle. And I'll try to put it at the same tilt, like that. This is going along our curve. This part was along our curve. So that's going to be our DL. It's part of our arc length. It's a little segment of the L. This slice here was along the radius. So this slice here is a DR. right? This slice here was along the circle. So it's like S equals R theta, but it's not R theta anymore. It's more like R d theta, because the angle is just a theta or d theta, not the full theta. We're calling d theta. So S equals R d theta. So we have dl squared. This is a right triangle equals dr squared plus r d theta squared. And if we're doing this with over d thetas, we do it like this. Oops. So that's like dl d theta squared equals dr d theta squared plus r squared, because the d thetas are going to squared thetas are going to cancel on that last term. And when you integrate both sides, well, take the square root. And then integrate from theta equals alpha to theta equals beta. You get that. I personally like going off the dx dt plus dy dt, because the triangle thing is like, you got to remember what everything is, draw a good picture, and like figure out what shit is. Like all integrals, from alpha less than or equal to theta less than or equal to beta needs to be continuous. That is an easily forgotten rule from our Calc 1. Do derivatives, we need continuity. That's what we want to take away from this page. I'm going to rewrite that on the next page. Sure everyone's caught up before we do an example. That's a square. It doesn't look like it very well. It's a square. Let's find the arc length. R equals cosine squared 1/2 theta, or theta over 2. For theta in 0 to pi over 6, pi over 3. Let's do pi over 3. So we're gonna need DRD theta there, right? So we got R. What is DRD theta? We got a chain rule going on, right? Because this is really cosine of theta over 2 squared. So we need to address the exponent first. So we'll bring the exponent down. And then we take derivative of the next thing on the inside. The next thing on the inside is the trig function. Derivative of cosine is negative sine. And then we gotta go inside again. Take the derivative of what theta over 2, we just get 1/2. So this just cleans up into negative sine theta over 2, cosine theta over 2. And now we'll do the integral. R squared should be cosine to the 4th theta over 2. And if I square this, it's going to be positive, and I'm going to have a sine squared theta over 2 and a cosine squared theta over 2. Then we'll have a d theta. So let's clean that up a little bit. I'm going to factor out a common term inside. If I factor out, they both have a cosine squared theta, right? Or theta over 2. If I do that, what's left behind is a cosine squared theta over 2 and a sine squared theta over 2. And then I got to do theta. If I put these two back together, I'm going to get cosine to the 4th. And put these two back together, I get a sine squared to cosine squared. Right? And who gives a shit that it's theta over 2? These are both the same angle. Cosine squared A plus sine squared A is 1. So I really just have the square root of cosine squared, and that's just cosine. So I integrate this, I get, what do I get if I integrate? It's gonna be a sine. And we've got to deal with the 1/2, which means having the inverse of that. And then we're going from 0 to pi over 3. So we have 2 sine pi over 3. Effectively, if I'm doing this, I'm multiplying each of these by 1/2 to get my thing that goes on the inside. This is 2 sine of pi over 6 minus 2 sine of 0 still. What's sine of pi over 6 though? 1/2. So this is 2 times 1/2 minus 0, just 1. Fun, right? Let's take a 10-minute break now because we're about to do area and that's going to take some time. So might as well take the break now. Okay, we're gonna take a look at doing area now. So there's a couple ways to look at it. I kind of like the easiest idea. They're both pictorial. But the easiest one is we've got like a circle. So if this is like d theta, then this region is like dA. A little piece of area with a little piece of theta. And they should be proportionally the same for like a circle. dA over pi r squared should be the same as d theta over 2 pi. A full circle for both. So dA d theta is pi r squared over 2 pi. Maybe I'll leave the dA by itself. dA is, looks like if we cancel out the pi's, we have 1/2 r squared and then the d theta. No, leave the d theta over there. If you happen to remember the area of a sector, it's A equals 1/2 r squared theta. And so when you take the derivative of this, r is constant on the area of a sector. So this is only in terms of theta, and you will get this when you take the derivative. That's the easiest way to remember it. Simplest portion of a circle. So dA equals 1/2 r squared d theta. We integrate both sides and we get A. Pull out the 1/2. We've got r squared d theta. Now, when we did it up here, r was a constant for the area of a sector. Here, r is a function of theta and it is not constant. Well, it doesn't have to be constant. The biggest pain in the ass for this can be finding thetas. Thetas or the boundaries or limits of integration. Couple ways this can be a pain in the ass if you're looking for the intersection of two curves. If you do it algebraically, you will find when, like, let's say we have R1 is a function of theta 1, R2 is a function of theta 2. You can find when R1 equals R2, but it may not occur, or this only shows when theta 1 equals theta 2 also. So it's the same R and same theta at the same time. Two curves can intersect, but at different thetas or different times. Like theta is just like a parameter t. If we did time, in general, you don't want things crossing at the same time because that means they're colliding. So this approach only shows collisions. If they were like actual things moving at the same time when they would hit each other, not all intersections. So graphically is usually the way to go. All right, so you guys ready for an example? The formula is fairly easy to remember. Let's go with do I want to do area yet? Let's where. This first example shows the problem with the system. We're not going to do an area problem with it though yet. I just want to show what we're talking about here. Like if we have R equals 1 minus cosine theta and R equals 1 plus cosine theta. one way to find intersections is set them equal to each other. They should be at the same R. So like R1 should equal R2. 1 minus cosine theta equals 1 plus cosine theta. And you do this, you get 0 equals 2 cosine theta. And where does that occur? Pi over 2 or 3 pi over 2. And if we sketch these two, these both look like cardioids. One of them does this and the other one does this. And the easiest way to, like cosine goes left or right, the easiest way to remember which one is which, it's when they have the same matching coefficients. Just plug in theta equals 0 and go, is it to the right or to the left? When theta equals 0, R1 would be 1 minus 0, which would be 1. Or not, sorry, 1 minus, not 0, 1 minus 1 is 0. So the R1 is doing this. That's my R1 curve. And my R2 curve, when I plug in theta, I get positive 2. So it's out here. So this is the one that goes like this. And they actually intersect right there. And those should be the same size, but I didn't do them very well. That's the R2 curve. So we can see they are intersecting at pi over 2 and 3 pi over 2 if you're sweeping out it radially. But they also intersect here. So it intersects, like when this one happened, this was when theta 1 equals 0. This is when theta 2 equals pi. They happen at different thetas when they hit. So it doesn't show this intersection. So you got to be careful with that. So let's look at one where we'll actually find the area. Find the area of the intersection. We'll say R equals cosine theta. And R equals 1 minus cosine theta. And I'll make a little R and or theta and R column here. And you know what? To save space, I'm gonna call this R1 and R2. And we'll use the same table, but use just different column. So this one should be easy. It's 1, 0, -1, 0, 1. Maybe we should slap in a pi over 4 just to see how it looks like in between. Let's do a pi over 4 on the list. Cosine of pi over 4 is √2/2, which is approximately 0.7. R2 is like doing 1 minus R1. This is like 1 minus R1. So 1 minus 1 is 0. 1 minus 0 is 1. 1 minus -1 is 2. 1 minus 0 is 1, and that's back down to 0. And that we already know it's a cardioid, so I'm not going to even bother with that pi over 4 on that one. So R1, we've got 0 degrees goes out. Like I need a radius of 2. I've got 0, 1. And then pi over 2, 0. That's not 0. That's 0. So pi over 4 is kind of like in between them, and that's like that. And then when we have pi, we have -1, which is back over there. 3 pi over 2 is 1. Nope, 3 pi over 2 is 0. I'm fucking looking at this wrong. You know what? Cover up the second column. Our theta is 0, r is 1, theta is pi over 2, r is 0. Theta is pi. All over here, we're doing -1, which is back here. Theta is 3 pi over 2, we're at 0. This isn't showing it very well, but it does do this. That looks shitty. Theta is pi, radius is -1. It's going that way. We need like a 3 pi over 4 in there. And the other one is doing 0, 0, 0, 1. This is the one that's doing this. So where they intersect is this. Let's set them equal to each other and see if we get angles that look like these points of intersection. So cosine theta equals 1 minus cosine theta. 2 cosine theta equals 1. Cosine theta equals 1/2. Theta is plus or minus pi over 3. That looks about right. Pi over 3, and if I drew it a little bit better, negative pi over 3. Are you guys with me so far? I'm gonna blow up one of these areas. Does it look like it's fair to say, looking at it, these look symmetrical? So if we find one, we just double it. So I'm gonna blow that up, that little, almost like a football, a little bit bigger. We'll do the one on top because I sketched that one. That's the theta equals pi over 3 line right there. But it's actually coming from here. And this line right here was the 1 minus cosine theta. And this line right here is the cosine theta. So as I go from 0 to pi over 3, I'm hitting this line. As I go out radially, I'm hitting that line. As soon as I cross pi over 3, I'm hitting the other line until I get to pi over 2. This is going from pi over 3 to pi over 2. And that's a little tricky. It looks like I drew a 45-degree angle, so ignore the angle of the picture, the tilt of the picture, but like the idea is there. We're hitting different functions at different times. So it's effectively like looking at two different parts. This has got to be the integral from 0 to pi over 3. We had 1/2 r squared d theta. 1/2. For this one, that's my r, so 1 minus cosine theta squared d theta. And then on this one, I'm going from pi over 3 to pi over 2. And on that one, my r is cosine theta. That's what's getting squared there, d theta. And this will just give us one wedge. So we need to double it. So maybe let's just put the 2 in front of it now. Let's double. Which is going to cancel out the 1/2, right? So I've got 0 to pi over 3. If I expand that, I've got 1 minus 2 cosine theta plus cosine squared theta d theta. And then over here, I got pi over 3 to pi over 2 cosine squared theta d theta. Anyone remember what we do to deal with cosine squared? Oh. Yeah, it's a power reduction. How do I do that? It is too. I'm going to start with, let's start with the cosine 2 theta formula. Since most people can't jump to the reduction formula, that is 2 cosine squared theta minus 1. It's plus, it ends up being plus. So if I add the 1 over and then divide by 2, so I've got 0 to pi over 3 of 1 minus 2 cosine theta plus 1/2 plus 1/2 cosine 2 theta d theta. I'm splitting that into 2 parts because we're going to integrate them separately. All right, so let's see. I got theta minus 2 sine theta. If I add these two together, I have 3/2. So that would be a 3/2 theta. I'll put that together right here. And then if I do this, I've got a sine of 2 theta, but I gotta divide by the 2. 1/4 sine of 2 theta. And that's from 0 to pi over 3. And on this one, I have 1/2 theta plus 1/4 sine of 2 theta from pi over 3 to pi over 2. All right, so doing this one, we have, I'm just gonna plug the shit in. And then I'll evaluate it separately. Because if I try to do it all at once, I'm gonna fuck this up. And that really sucks while you're lecturing. So that's my green part. Looks like for the green part, I have a pi over 2. Sine of pi over 3 is √3 over 2. And then times 2 is minus √3. And then sine of 2 pi over 3 is the same value, √3 over 2, I've got √3/8. All of those are zeros. Right? That's all zero. We'll take a look at the blue now. Then we have plus 1/2 pi/2 plus 1/4 sine of 2 times pi/2 is sine of pi. Minus 1/2 pi/3. Let's see. Plus 1/4 sine of 2 pi/3. So that's a plus pi/4 plus 0 minus pi/6. And then minus a √3/8. So I've got pi/2 plus pi/4 minus pi/6 minus √3. If I get a common denominator, this is 6/12, 3/12 minus 2/12 times pi. What is that? 7 pi/12 minus √3. Whatever the hell that area is in a calculator. Can't be very big. It's a small little wedge. Zero 0.100 to 3 decimal places. Now we'll go to 2 decimal places. That way I don't have to round. Not a very big intersection, right? I promise you, if you try to ask ChatGPT about this, they get fucking confused. They're like, what do you mean inside both of them? It does some weird shit. The next one, I'm going to show you what ChatGPT said. We're going to solve it by ourselves first, and I'm going to show you what it said. And how many times I had to say, no, that's not it. Try again. All right, next one. We've got R equals 2 cosine 4 theta. Find the area of a single petal. When we have n theta inside, it makes a rose. When n is even, it makes an even amount of petals or doubles it. So there should be 8 petals. It's gonna make a petal here, 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 here. And it's also got ones along the diagonal. And if I drew this better, there wouldn't be any overlap. 4 petals. When you're graphing them, it does not go in that order. Kind of does this weird fucking bounce around while you're doing it. So the easiest petal that might be to work with is this one. We just need to figure out what angle that is. And we should have the same angle over here, which would be negative question mark. So what happens when I do theta equals 0? I'm getting r equals 2 cosine of 4 theta, 2 cosine of 4 times 0 is 2. So theta equals 0 is giving me that point. What value do I have here for r when I'm back here? If I'm at the origin, it's going to go like this. It's going along this direction. At this point, I have r equals 0 right there. So we really want to find where does 2 cosine 4 theta equals 0, and I can find what that theta is. Does that make sense? Well, divided by 2, I've got cosine 4 theta. What does this have to equal to get a cosine of 0? Cosine of what is 0? Pi over 2. So theta equals pi over 8. We should be going from negative pi over 8 to pi over 8. There's actually a simpler way to figure that out. How many petals is there? There's 8 petals. How many radians did it have to go through to get that? 2 pi. So 2 pi radians for 8 petals means each petal has a full pi over 4. And if I know the 0 cuts it in half, I have to have a pi over 8 this way and a pi over 8 this way. Does that make sense? To end up with a total of pi over 8 plus pi over 8. So pi over 8 go in each direction. So I'm going to do negative pi over 8 to pi over 8. We're doing 1/2 r squared, which is going to be, I'll actually write that in before we square it, d theta. So we've got 1/2. I'm going to make this a little bit easier, and I'm going to say u equals pi over 8 and just go from negative u to u. I'm tired of writing pi over 8 on the integral. This doesn't make the problem any easier, it just makes the integral look prettier. We've got 4 cosine squared 4 theta d theta. If I move the 4 out, I've got a 2. And this turned into 1/2 plus 1/2 of cosine of twice the angle. So 8 theta in there, d theta. So if I integrate this, I've got from two times. Oh shit, actually, before I enter, why don't I just move the 2 in and make this both into a 1? Sound good? Get rid of extra numbers here. This becomes theta plus 1/8 cosine 8 or sine of 8 theta. And we're going from negative u, which was negative pi over 8, to positive pi over 8. So I've got pi over 8 plus 1/8 sine of 8 times pi over 8 is pi minus negative pi over 8 plus 1/8 sine of negative pi. Which is crazy because this ends up being pi over 8 plus pi over 8, which is pi over 4, which is what I said was the number of radians earlier. It's just coincidence. That's my area of one petal. So all 8 petals. I'm using DAL. Petal is T. TAL. 8 petals would be 8 times pi over 4 or 2 pi. Square units. I didn't specify the units. Anybody else still copying it? Michael is. I'm going to show you what ChatGPT did on this problem. Like, I fucking did like share link. I sent it to Professor Allen. And he's like, oh my God, if the student isn't aware that it's wrong, they just throw so much math at you that it looks right. Let me change Zoom so that the video shows this. I told it find the area of one loop of r equals 2 cosine 4 theta. It knew the formula. And it says it figured out each loop occurs over an interval of pi over 4 radians. That's what I said. And so it said for a single loop, when r is greater than 0, we've got theta equals 0 to pi over 8. So it only did half a fucking petal. And it goes through and it does the whole thing at half a petal. Gets down here and says the result is pi over 8. I tell it that isn't correct. You're absolutely right. I appreciate your patience. Let's try this again. Look what fucking angle I got again. The exact same goddamn thing. I don't know how many times I would have had to say, no, that's not it. I ended up just going, no, let's try. Wait. It doesn't show it. It's missing the text. I said use theta from, I said the angle isn't 0 to pi over 8. I think that's what I said. And that's where it said, oh, thank you for catching that. Let's fix that. Does it say it anywhere here? Oh, here it goes. So there was a couple prompts where it still got pi over 8. Here I still tell it doesn't go from 0 to pi over 8. You are correct again. Finally, it recognizes the pedals go from pi over 8 to 3 pi over 8, going around. So negative pi over 8 to pi over 8 is what we did. It does 0 to fucking pi over 4, which happens to get half a pedal from 2 different pedals, giving you the right area, but it's not the area of one pedal. It's not the area of a single loop. It's half the area of 2 loops. So it ends up getting you the pi over 4, but it was still fucking wrong. And if you're not looking for it, if you don't graph it or anything like that, ChatGPT is not your friend while trying to study calculus. Like, it's just not.
So are they always gonna be evenly spaced though, or would
When n, what do you mean?
Oh, no.
Oh yeah, for a rose it is.
Only when.
No, for any of them. When n is even, it's just double the pedals. When n is odd, like if n equals 3, the tips of the pedals are 120 degrees apart. In fact, let me go back over to the camera and do that. So if we had like cosine of 3 theta, it says, okay, there's 3 pedals. And so one pedal is right here, and 2 pi over 3 or 360 over 3 is 120 degrees, puts a pedal there and a pedal there. They are evenly spaced to the endpoints. Sine starts off at the diagonal. It's kind of weird. Let's do, oh shit, we don't really have the time. I challenge you. This is easy. We'll show the picture. Find the arc length and area of r equals 4 sine theta. Using the calculus. Four, 2. It's a circle of radius 2. So show for the entire circle. For 0 to 2 pi, say that. When you're done, you should get arc length is 2 pi r, which is 4 pi. And when you're done, your area is pi r squared, which is also 4 pi. But do them using the whole polar, what we just did, we're covering in this chapter, get them that way. That's a little challenge for you. Other than that, that's it for these topics. Ainsley's got a good review up on Discord if you wanted to see like a good practice exam where you can kind of expect. The first one on her exam is pretty easy. It's like a joke of easy. It might be a little bit harder than that, but that's it. That's all we've got. Have a great Thanksgiving. If you're studying over the weekend and you want to come ask questions, I'm at Mesa from 8 to 2 on Saturday. If you don't know where that is, email me and I'll tell you. Other than that, have a great weekend. Try to get some math done. You're kind of forced to with a test on Monday. You don't have a way out of this one. Yes, sir.